Welcome to the Cal Corporation's series of videos about software engineering. The topic of this video is the S.F.I.N.A.E technique for conditional compilation. Before proceeding, make sure that you have already watched these other videos first. This convoluted code is negating a value of 11 by storing that value as a data member in some object and then passing that object to a templated function called negate. That templated function can be used because it can specialize its template parameter t as that CR negator type of object. Now, let's complicate things even further. Let's abstract that data member's type by programming a type alias for it. Templating code can sometimes confuse a compiler. It won't let you compile this code because it doesn't know for sure what that T type is going to be for all specializations of T. Will it be a static data member or a nested type alias? We know that it's always going to be a nested type alias, and so it's safe to use it as negates return type. But we need to reassure the compiler that T type is a nested type alias. Reassure the compiler about that by preceding it with the keyword type name. Now, consider what happens when negate gets called this way. Function overloading is occurring here. The parameter 11 could match with parameter type constant reference to int, which is what the first implementation would have if that template specializes t to int. Or the parameter 11 could simply match with int, which is the second implementation. While first considering that first overload option, an old compiler might stop, triggering a compiler error, because there is no such thing as int type. But modern compilers instead follow a principle called substitution failure is not an error. When these modern compilers encounter the int type issue, they don't suddenly give up on compilation. Instead, they silently eliminate int as a specialization option for T, and then carry on. In this case, there would be no other specializations possible for the template, but function overloading can simply match 11 with int and use the second implementation. What about if we make this change? Remove the troublesome T type abstraction from the function signature. Now we know all compilers, obsolete and modern ones, will successfully specialize T as int, and all compilers will use the first implementation for their function overloading. But let's now try to use the T type abstraction for defining a local variable. Trying this will cause all compilers, obsolete and modern ones, to abort their compilation and report a compiler error when they encounter the invalid int type. The S.F.I.N.A.E principle only ever saves us while inspecting function signatures. It does not save us from any problems that might arise within the function body. For this next example, imagine some situation where the programmer wanted to write a generic do function. But unfortunately, he did need to assume that his AI int parameter was some kind of integer type. To avoid any problems that would be caused by that assumption, we want some form of conditional compilation. We don't want this templated function to specialize t to any non-integer types. The programmer might also have another implementation of do, but this time needing to assume that his parameter was some kind of object type. We know that there are predicate traits that could tell us at compile time whether or not the type is integer or object. But how do we use them here? How do we cause conditional compilation? There is an advanced programming trick called the dummy pointer default template parameter trick. It will accomplish our goal. Within this built-in enable if is a nested type alias. Of course, it's called type. But that nested type alias only exists if enable if's own first template parameter specializes as true. But where does that true or false value come from? Use a predicate trait to create that true or false value at compile time. So this long code fragment will essentially be the same thing as merely typing a t, but only for specializations of t that are integers. For other specializations of t, this code fragment won't even be defined. Here, we don't really care about this second template parameter. What we are doing is exploiting its S.F.I.N.A.E side effect. For an integer specialization of t, that code essentially becomes as if we had programmed type name t star equals sign null pointer. And that's a valid way to write a default template parameter, which we ignore and never use. But for some kind of non-integer specialization of t, this attempt at a nested type alias won't even be defined. The S.F.I.N.A.E principle says that's okay, there's no error. It just silently eliminates the possibility of specializing t as that non-integer type. This achieves the conditional compilation that we needed. Technically, there isn't any function overloading going on here. Because of the conditional compilation, only one or the other implementation exists for a given template specialization. Again, C++14 provides an unimportant syntax shortcut. We just discussed a trick for conditional compilation. That same trick could be used in the specification of a return type. This is negative is a templated function. Your client code could generically pass some data having any numeric type, and the function will then return a Boolean. But if you try to pass it some non-numeric thing, then the conditional compilation will cause that function to not even exist. And you'll get an appropriate compiler error because you shouldn't be trying to call it that way in the first place.